All right, today we're diving into a chemical family that pretty much runs our world from behind the scenes. We're talking about alcohols, phenols, and ethers. They're all part of what we can call the oxygen family, and their tiny little differences are the reason we have everything from powerful medicines to simple wood polish. So let's dive in.
So let's start with a little riddle. Think about it for a second. What could wood polish, the antiseptic you use for a cut, and the sugar in your coffee possibly have in common? I mean, they seem totally unrelated, right? But believe it or not, from a chemical standpoint, they're all deeply connected.
And that connection brings us to our first idea. These guys are really chemistry's unsung heroes. They're the kind of compounds that are absolutely essential to our daily lives, but they're always working in the background, Out of sight, out of mind.
Okay, so here's the big reveal. They're all powered by organic compounds that are built around one single crucial atom, oxygen. That spirit in your wood polish? Yep, that's ethanol, which is an alcohol. Those antiseptics? A lot of them rely on phenols. And stuff like sugar, cotton, even paper, they're all made of compounds that have this special little group, the hydroxyl group, or OH. See? It all comes back to that one oxygen connection.
So it's time for the formal introductions. Let's meet the stars of our show, the oxygen family, and really get to know what makes each of them tick. We're going to treat them like three main characters in a story. First up, we've got alcohol. Now, what makes an alcohol? An alcohol is that it has a hydroxyl group, that's our OH, and it's attached to what's called an aliphatic carbon chain. And don't worry about that fancy word. Aliphatic just means the carbon atoms are in a straight line or a branched chain, not a closed-off ring.
Next up is phenol. Now, you might be looking at this and thinking, hey, that looks really similar. And you're right, it's also got that OH group. But here's the huge difference. It's all about location, location, location. Instead of a chain, that OH group is stuck directly onto an aromatic ring, like a benzene ring. And that one tiny change, it gives phenols a totally different chemical personality.
And our third and final character is the ether. Now, ethers kind of break the rules a little bit. Instead of having an OH group hanging off the side, the oxygen atom itself is right in the middle, acting like a bridge connecting two different carbon groups. You can see it right there in the structure, R-O-R. That oxygen is the centerpiece.
So let's just quickly put it all together. For alcohols, you've got that minus OH group on a carbon chain. For phenols, it's the minus OH group on a carbon ring. And for ethers, the oxygen atom itself is the bridge. Simple, right? But where that oxygen atom is placed, well, that changes everything.
Okay, so we've met the family, we know who they are, but where do they actually come from? Let's figure that out now, and take a look at how these incredibly useful compounds are made.
For alcohols, a really common way to make them starts with something called an alkene. That's just a molecule with a carbon-carbon double bond. All you have to do is react it with water, with a little acid to help things along. The water pops open that double bond, and boom, just like that, you've made an alcohol. Now, phenols, they're a different story. Industrially, on a massive scale, pretty much all the world's phenol is made from this one specific hydrocarbon called cumene. It's a really clever process. And ethers have their own ways of being made too. See, every member of the family has its own unique origin story.
Okay, so we know who they are and we know where they come from. Now for the really fun part, their chemical personalities. Let's dig into why their structures make them act in such specific and honestly very different ways.
A perfect example of their different personalities is boiling point. Alcohols and phenols have these surprisingly high boiling points for their size. So why is that? Well, it's because that little OH group lets them do something called hydrogen bonding. You can seriously just picture the molecules holding hands with each other, forming this strong network that's tough to pull apart. Ethers, on the other hand, can't do that, so their boiling points are way low.
But that brings us to a really crucial question about their personalities. See, both alcohols and phenols can act as weak acids. They can give away that little hydrogen from their OH group. But phenols are dramatically stronger acids than alcohols. So what's the deal here? Why?
The answer, in one word, is stability. Think about it. When an alcohol loses its proton, the negative charge it leaves behind is just stuck. It's stuck right there on that one oxygen atom, and it's not a very stable or happy situation. But when a phenol loses its proton, something kind of magical happens. That negative charge gets to spread out or delocalize over that entire aromatic ring. It's like a huge sigh of relief for the molecule. Sharing that burden makes it incredibly stable.
So, does this stability thing really make a difference?
Oh yeah, a massive one. Because that resulting ion is so much more stable, phenol is much happier to give up its proton. We're not talking a little more acidic, we're talking about 1,000,000 times more acidic. No, that's not a typo. 1,000,000. The power of spreading out that charge is just mind-blowing.
Another classic reaction for alcohols is something called dehydration. And it's pretty much exactly what it sounds like. The molecule loses a molecule of water. It's a neat little process. First, a proton from an acid hops on to the OH group. Then, that whole group leaves as a harmless water molecule. And finally, everything rearranges, a new double bond forms, and you've turned your alcohol into a whole new compound, an alkene.
So we've covered the theory, right? We've seen their structures, we've gotten to know their personalities. Now let's bring it all home. Where do you actually see these compounds in real life? Let's look at the oxygen family's greatest hits.
One of the absolute biggest deals for this family is a reaction called esterification. And trust me, you've experienced esters your whole life. You know that sweet smell of bananas or fresh strawberries? That's esters at work. But they're not just about nice smells. They are also absolutely crucial building blocks for life-saving medicines. And this leads us to probably the single most famous example of this chemistry on the entire planet. It's all about making aspirin. You take a compound called salicylic acid, which has a phenol group on it, you react it in a specific way, a type of esterification, and what you get is aspirin, one of the most important medicines ever discovered. It's that simple and that profound.
And phenols are definitely not a one-trick pony. They're the starting point for a whole bunch of other famous and really useful reactions. Think of things like Kolb's reaction or the Reimer-Tiemann reaction as special tools in a chemist's toolkit. They allow chemists to add new bits and pieces onto the phenol ring, creating all sorts of new molecules for things like fragrances and other medicines.
So, when you look around, from the medicine in your cabinet to the paper in your printer, this family of oxygen-based compounds is just everywhere. They really are the unsung heroes making so much of our modern world possible. And it really makes you wonder, doesn't it? Knowing how powerful and versatile they are, what amazing new things are we going to build with them next?